we know that one of our bounds is infinite here. So right away, we're going to have to change this from an improper integral to a proper integral by using limits. I'm going to rewrite the problem as the limit as a approaches infinity. And the choice of letter here doesn't matter. I always choose a the first time, and if I end up needing two of them, I use b. And we're going from 0 to a. Whenever we're dealing with infinity, we don't have to put the coming from the left or coming from the right. There's only one direction to approach positive infinity from, and only one direction to approach negative infinity from. Yesterday, someone asked about sort of when you look at an integral, how can you get better at seeing what to do? This is a classic example of a rational function with exponential pieces in it. And one of the things that comes up a lot in these kinds of problems is this trick where we really want to think about that e to the 2x term as being e to the x with the whole thing squared. If we kind of change our mind frame to think about that e to the 2x in this other way, I think then it's easier to see the u substitution in here. Now when I look at this problem and I'm thinking, okay, algebra, trig are a mixture of stuff. It's a mixture problem because I have this e to the x term in it. My first option is still going to be to check for a u substitution. And in this case, the derivative of e to the x is e to the x. So I'm going to have that u substitution in here. If I let u be equal to e to the x, then du is e to the x dx, which I have. Got that e to the x dx. And then remembering that we're going to need to switch those limits of integration because we're making that u substitution. Secretly, the 0 and the a right now are x equals 0 and x equals a. When we do the u substitution, we need to convert both of those bounds to u. When x equals 0, u would be e to the 0 or 1. When I write that over here, I have to keep it in the same place so that x equals 0 was at the bottom, and I need to put the u equals 1 at the bottom. When x equals a, u would become e to the a. Because the a was at the top, my e to the a will come up here. And I've still got that limit as a approaches infinity out in front. When we do the u substitution, the e to the x dx, that's all turning into our du. And then our denominator, that's u squared plus 3. I mentioned before, certainly when we were talking about 4.6, and then I mentioned it again yesterday, that our book actually gives more generalized forms for some of our antiderivatives. When I look at this, I'm immediately thinking arctan because I have 1 over u squared plus a number. Once I know that I'm thinking about arctan, we have two options. We either manipulate this to look exactly like the arctan we want, or we memorize the more generalized formula for antiderivatives that look like this. In the index reference sheets of our textbook, this comes from reference page 6, which is the table of integrals. The generalized form for something that looks like du over a squared plus u squared is 1 over a tan inverse of u over a plus c. And that's the generalized form that I choose to memorize so that I can go straight from something that looks like this to something that looks like this. The only catch here is that this formula implies that we have a number squared plus u squared. This 3, it's not a perfect square at the moment. So there's an added step to think about that 3 as being the square root of 3 squared. Now I have this form of u squared plus a squared in my denominator, and I can utilize the formula. I just realized that having an a here, this a and this a are not the same. Hopefully that's clear. This formula just happens to use an a. Okay, coming back to our problem at hand here. So we would have the limit as a approaches infinity, and this would become 1 over the square root of 3 tan inverse u over the square root of 3 plus a c, but I don't need the plus c. This is a definite integral. So I'm going from u equals 1 to u equals e to the a. Plugging in our limits of integration, I'm looking at a limit as a approaches infinity, 1 over the square root of 3 tan inverse of e to the a over the square root of 3 minus 1 over the square root of 3 tan inverse of 1 over the square root of 3. Now we're ready to take our limits. As I plug in infinity for a, e to the infinity, like we were talking about before, e to the infinity is infinity. Tan inverse of infinity is pi over 2. And to help us see why tan inverse of infinity is pi over 2, I'm going to need to squeeze a little bit of space in here, so I'm going to get rid of our generalized formula. A graph of tangent has vertical asymptotes at pi over 2, sorry, negative pi over 2 and pi over 2. And the graph almost looks like a cubic in between. When we're looking for tan inverse of infinity, that's asking us at what angle is tangent approaching infinity. And the angle where the graph of tangent approaches positive infinity is pi over 2. So evaluating this limit, that's going to be 1 over the square root of 3 times pi over 2. This next piece, I need to find tan inverse of 1 over the square root of 3. And I guess I'll squeeze in another little box here. This is asking us what's the angle where tangent is 1 over the square root of 3. Well, I know that that square root of 3 is coming from our 30, 60, 90 triangle, or an equilateral triangle that's been cut in half. When I think about that equilateral triangle, I label my sides 2 and 1 because I've cut it in half, and I know that height is the square root of 3. This corner was that 60 degrees, or pi over 3, which makes this corner half of that at pi over 6. When I'm looking, so now I'm looking for the angle where tangent is equal to 1 over root 3, which means my opposite side has to be 1 and the adjacent side would have to be root 3. So that's an angle of pi over 6. I've got 1 over the square root of 3 times pi over 6.